Hi, this is Nazmul. Today I am going to present my CVPR work, a curriculum learning aided self-training framework for efficient source-free domain adaptation. In this work, we address the task of source-free domain adaptation where we don't have access to the source domain data while adapting to the target domain. In recent state-of-the-art methods, they follow self-training strategy where they use a memory bank and a nearest neighboring strategy to refine the pseudo labels, but they struggle under resource constraint scenarios. In our work, we propose to completely remove the memory bank and instead propose a selective pseudo-labeling technique which separates the pseudo-labels into reliable and unreliable groups, and using three different loss functions we learn from these reliable and unreliable samples. And moreover, we use curriculum learning strategy that prioritizes learning from reliable samples first and propagate the labels to the less reliable ones later, and we obtain SOTA performance on image classification, semantic segmentation, and online test time domain adaptation. The rest of the presentation contains the following: an overview on domain adaptation, motivation and contribution of our work, our proposed method, experimental results of our method, and the conclusion. In domain adaptation, a deep neural network is trained on a source dataset with labels and adapt to a target dataset that is also with the labels. So usually this is known as supervised domain adaptation. And in unsupervised domain adaptation, we have labels for the source domain data, but we have to adapt the model to target domain data without their labels. So there is an updated version of the unsupervised domain adaptation, which is source-free domain adaptation, where we don't have access to the source data while adapting the model to the target domain. And since we don't have access to the source data, there is no way to estimate the domain shift between the source domain data and the target domain data. And it is the most challenging domain adaptation setup, and it struggles under large domain shift. To explain the motivation behind our work, we first give a brief overview on the working principle of state-of-the-art techniques, which follow self-training strategy where the teacher model provides pseudo-label for the student model, and depending on the domain shift between the target domain and the source domain, the quality of these pseudo-labels can vary. And if the quality is bad for the pseudo-labels, then the student model performance of the student model will deteriorate. And to improve the pseudo-label quality, existing SOTA techniques use memory bank and nearest neighboring technique for pseudo-label refinement. So basically, these methods use memory bank and they take the n nearest neighbors predictions to calculate the pseudo-label of a given sample. Now the challenge with the nearest neighboring technique and memory bank is that in a nearest neighboring technique, the neighbors can be misleading based on the domain gap between the target and the source domain data. And since we are calculating the pseudo label based on the nearest neighbors prediction, the refined pseudo labels will be mostly noisy, and this will severely impact the classes with large domain gap. As we can see in the picture that classes like skateboard or truck, there is a large number of neighbors that are misleading or noisy. And also this method struggles under memory resource constraint and limited computation. We have addressed the issue of classical pseudo labeling where we had less accurate pseudo label and poor performance due to the bad quality of pseudo labels, but it had also the advantages of no memory bank and computational efficiency. And in memory based pseudo labeling, which has been used by previous state of the art methods, it has the advantages of more accurate pseudo label and state of the art performance, but it has also the disadvantages of noisy neighbor issue and memory inefficiency as well as computational expensiveness. Now if we want to design a new method, we obviously don't want to have these disadvantages, and we would like to have the advantages, and that is exactly what we propose in our technique, where we don't use any memory bank and we also produce more accurate pseudo label than the current state of the art methods. Our intuition is that we should not use all the pseudo labels since their quality cannot be guaranteed, and for some samples the generated pseudo labels are always wrong, and memorization of these unreliable or noisy pseudo labels can be bad for the performance. And that's why we want to separate the pseudo labels into reliable and unreliable groups. But there is a concern that can we identify the unreliable ones and separate them from the reliable ones. So we use a selective pseudo labeling strategy where we get the pseudo labels from the teacher model and we separate them into reliable and unreliable group, and we use cross entropy laws for the reliable group of pseudo labels and label propagation laws for the unreliable pseudo labels. And we also use the unsupervised contrastive laws to learn unsupervised features from all of the samples. For separating the pseudo labels into two groups, we first apply L number of augmentations and we get the predictions from the teacher model, and after that we take the high confidence pseudo label and the low uncertainty pseudo label as the reliable group of samples, and the rest of the samples are unreliable samples. Due to our selective pseudo labeling strategy, we can see that over the training average confidence score increases and average uncertainty score decreases, and we are selecting more reliable samples with better precision, and the overall effect can be seen on the average accuracy of the model, which see a steady increase over the training. And we experiment on both image recognition task and semantic segmentation task. For image recognition, we use 4 different datasets: Office 31, Office Home, Business C, and DomainNet. And for semantic segmentation, we use 3 different domain adaptation tasks: GTA5 to Cityscapes, Cynthia to Cityscapes, and Cityscapes to Dark Zurich. For image classification results, we can see that our method obtains state-of-the-art performance for all of these 4 datasets. Notably, we obtain 1.2% performance improvement over previous SOTA on DomainNet. And for semantic segmentation dataset, we obtain 1.1% improvement for Cynthia to Cityscapes domain adaptation task, and we obtain 0.8% improvement for Cityscapes to Dark Zurich. And here are some qualitative visualization where we show that our method surpassed the current SOTA baseline in semantic segmentation tasks. In summary, we address the source tree domination problem. Our proposed method is based on self-training framework. We do not use any memory bank for pseudo labeling. Our method is simple but highly effective, and we achieve SOTA performance on several domain adaptation benchmarks.